Now we're going to talk about the idea of a reduction potential. So what we're interested in determining is the potential of the overall cell. And how we're going to do that is we're going to follow this idea of breaking the overall cell into half reactions. And these different half reactions are going to be composed of different compounds, elements that are going to have different tendencies to oxidize or to reduce. And those different tendencies are going to combine to not only tell us what is the redox or the reduction with the oxidation, and what the overall potential is. So each half reaction here, for example, in my silver, if I'm doing a reaction of silver and copper, the silver is doing reduction, and we could assign that the potential for silver to do reduction is, say, plus 0.8. Copper is doing oxidation, and the potential for that is negative 0.34. So when we look at these numbers, again, positive potentials show a tendency for spontaneous. So in this case, the silver has a tendency to be spontaneous. One of the ways we can think about this is silver cations want to take electrons and become silver solid. Conversely, we have a negative side over on the copper. That tells us that copper atoms tend to not want to lose electrons. But it's only negative 0.34 volts, which is outweighed by the 0.8 volts that comes from reducing the silver. So the silver kind of wins in this battle. It's the stronger agent here. It pushes reduction, and copper can't really resist oxidation that well. So when we're talking about these half reactions, in this way, we can kind of use a lot of shorthand. We use the vertical lines that we saw with cell notation, where we basically put reactant vertical line product. So this kind of overall implies the half reaction, where copper becomes the copper 2+. So we want these numbers. We want half reaction potentials. You can't just measure the potential of a half reaction because half reactions don't happen on their own, right? You need to have two half reactions, put them together to determine a whole reaction potential, or whole cell potential. So what we do is we just choose one of our half reactions and claim that this thing is going to have a half potential of 0. And it's what's called the standard hydrogen electrode. That is the reduction of H+ into H2. And so this is just a process where you're doing the reaction of hydrogen. Basically, you're running this reduction. You run it standard, implies that you're at 1 molar concentration of your H+, you're at 1 bar pressure of your H2. So everything is under kind of standardized conditions. You could then basically pair any other half reaction with hydrogen, and then you would say that the contribution from hydrogen is 0. So that means whatever you measure for the cell potential, you just assign to the other thing. So one of the things to note, these reduction potentials are only meaningful in a relative sense. So we can have tables upon tables upon tables of reduction potentials. So here you can see you have all sorts of reactions. You got things like fluorine, aluminum, tin, iodine, all sorts of reactions that are, all of these are reduction half reactions. They're all written as reduction. Electrons are in the reactant of every single one of these. And then you have the reduction potential, basically the tendency for this reaction to happen. And so these are tabulated for any sort of half reaction that anybody's ever thought of, because they always pair it with hydrogen to see what the potential is. So when we look at these kind of numbers, again, positive implies a stronger tendency to happen. So everything here that has a positive number for the potential, all of those half reactions have a stronger tendency to occur as reduction than the hydrogen process. And then everything below it has a weaker tendency to occur. That doesn't mean they won't happen as reduction. These are all relative orderings. There are plenty of half reactions that are negative down there that could still happen as reduction as long as they're paired with something that's weaker. If we look at this kind of rankings, then we can see that F2, fluorine, really wants to become fluoride. This is consistent with previous ideas that we've learned about, fluorine being really reactive. The halogens are really reactive on the periodic table. Fluorine really wants to react, really wants to be in, compounds and all this kind of stuff. And then fluoride is really strong as, an ion, all these ideas. On the other hand, Li plus really doesn't want to become lithium. Again, consistent with the idea that the alkali metals tend to be really reactive and tend to form +1 cations. They readily form these cations, and then they don't do any chemistry because they're really stable as those cations, lithium being extremely so. And so all of this follows trends, ionization energy, electron affinity, all of those ideas of atoms wanting or not wanting to gain or lose electrons. So we can use these reduction potentials to make explicit predictions about which half reaction is going to do reduction and which is going to do oxidation in any cell. Namely, whatever half reaction has a more positive reduction potential will do reduction, because that's a stronger tendency to undergo reduction. That will be the cathode. So if we look at, for example, the silver and copper, Ag plus has a more positive reduction potential. That's the 0.80 that we saw before. Copper 2 plus, also a decently strong potential, 0.34. But it is still lower than 0.8, right? Lower than the potential of silver. So the silver plus has a stronger tendency to reduce than the copper 2 plus, meaning that silver is going to win this fight, meaning that it is going to be the half reaction for reduction. So if silver is the cathode, copper has to be the anode, right? That means copper has to switch. It has to change from reduction into oxidation. And so that means your electrons would become the product. The potential for oxidation, we can see, is just the negative of the potential for reduction. We see the sign of the potential is going to change when we swap it from reduction to oxidation. Basically, we're just changing, well, we're asking what is the likely thing? Because, yeah, copper kind of has a tendency to gain electrons, but it kind of really doesn't have a tendency to lose electrons. So we can use these ideas to predict cell potential for any process based on if we know the anode and the cathode. So it's going to be reduction potential of the cathode plus oxidation potential of the anode. Functionally, you don't really see oxidation potentials, so we just think about it in terms of reduction potentials. So it'd be the reduction of the cathode minus, reflecting the fact that you're changing the sign, the reduction potential of whatever the anode is. One thing that we're going to get from this, E cell that you're predicting over here better be positive, because that indicates spontaneity. If you've gotten a negative potential for your overall cell potential, that would be the non-spontaneous direction. That is what does not happen. And again, reduction potentials are what we always tend to see tabulated. And so that's why we want to use those values. I do want to note that, when we're talking about, say, stoichiometric coefficients or the N terms that we've seen previously, none of those are coming into play here. We don't care that, in this case, silver and copper, one is a 1 electron process, one's a 2 electron process. That's fine. We just use the potentials straight out the table. They're already they're already normalized because it's per coulomb, which is kind of per electron. So that's already being cooked in. So let's look at an example. What is E cell not for the cell composed of the half reactions Al3 plus to Al and Al2 plus to, Fe2 plus to Fe? All right, so what is E cell? A cell composed of the half reactions Al3 bar Al and Fe2 plus bar Fe. So one of the first things we're going to do is kind of parse out what these meanings are. Al3, we've got a vertical line Al. So what that means is we'd be looking at plus. That is basically just an arrow for product. But what you're not showing is it's not balanced. There's no electrons that are explicitly included because it's kind of assumed that you can figure out what they are. Same thing with the Fe2 plus becoming Fe solid, and then you would add 2 electrons to that. So we can see that these are both written as reductions, which is a standard practice. You just say these are reduction reactions, or we think about them as reduction reactions, but we're kind of just we say these are the half reactions as reduction, even though not one of them is going to swap. One of them has to be oxidation. So in order to figure out which one, we need to look at a table of reduction half reaction potentials. And so I got aluminum and iron. And so basically what I do is I just find those. So we want to be careful. This is Fe3 plus becoming Fe2 plus. We don't want that. We want Fe2 plus becoming Fe solid. So Fe2 plus becoming Fe solid. It's hard to read across. So negative 0.45. So E red naught is equal to negative 0.45 volts. Aluminum, down here, aluminum 3 to aluminum, negative 1.66 volts. So these reduction tables are always available. There's one posted on Blackboard, this one. It's posted on Blackboard. So I encourage you to take a look at it, use it while you're working through any of these problems. There's also one in the book. Sapling has a huge potential table, so you can always use those, always have those available. So I've got these two values. What I want to do is I want to look at which one is lower. The lower or less positive value is less likely to do reduction. There's less of a potential to do reduction here. So this is lower. That means it flips. It's going to become oxidation. So what that means is that the overall cell potential that we wanted is going to be equal to the reduction potential of the Fe2 plus that we wanted minus the reduction potential of the Al3 plus. Because we're still going to use the negative 1.66 because it's just, that's where we have the negative sign out there. So we can just use this value, or you could switch the sign and make a positive. It'd be accomplishing the same thing. But we plug in our values. 0.45 volts minus negative 1.66 volts. That'd be equal to 1.21 volts. So, when we're looking at this, just because we see a negative potential for a reduction potential doesn't mean that this can't do reduction. This iron is still going to do reduction. It doesn't necessarily, this negative just means it has less of a tendency than hydrogen, right? That standard hydrogen electrode. But it still has a much higher potential, or higher tendency than the aluminum, which is way weaker than hydrogen, and therefore also weaker than iron. So this negative doesn't mean it can't do reduction. It just means it's less likely than hydrogen. It's all relative here. This is a much lower potential. We get to the 1.21 overall volts. That is another video down. Looking for more questions on participation 1111. See you in the next video.